very glad to have Po-Ling Loh from Wisconsin-Madison, who's going to talk to us about community recovery and weighted stochastic block models.
Okay, well, thanks very much to the organizers for inviting me here. I'll actually be in Cambridge for a longer period in the springtime, so it's great to sort of see the Institute and experience Cambridge. So I'll be talking about some work that I've done together with a postdoc, Min Shu, who is currently the department postdoc at Wharton at UPenn. So he did his PhD with John Lafferty, and you'll see some aspects of shape-constrained estimation and non-parametrics, which is what Min's expertise is in. And then Varun is a colleague and collaborator of mine, and he's an information theorist. So you'll see some sharp threshold phenomena in the discussion. And I should say that I chose this topic to talk about because it seemed like it would be most widely of interest to the audience. It's also my first time giving this talk, so I'm sure I'll learn something in the process, and hopefully you will as well. Okay, so I'll begin with an introduction I'll try to introduce stochastic block models briefly because I feel like it's something that everyone has sort of heard of to some extent. I'm going to focus on the formulation of weighted stochastic block models, which is the focus of our work. And then I'll discuss certain algorithms and analysis that we first conducted for the case of discrete weights, and then how we were able to generalize this to continuous weights. And then I'll have some remarks on the overall procedure at the end. So let's begin with introduction. So the goal of the problem is to perform community recovery. So we observe a graph, and the nodes are parts of underlying communities, but we only see the connectivity. And the goal is to, without noticing that certain nodes are colored black and certain ones are white, to just look at the connectivity or look at the adjacency matrix and partition it into communities. Of course, it's helpful if there is a difference between the density of edges within the same community versus between communities. So if there's more connectivity for nodes in the same community, sometimes that's called homophilic or assortative. Otherwise, it's disassortative or heterophilic. And the important thing to emphasize is that you can only really expect to do this community recovery if there is a difference between the types of, between the probability of edges sort of within versus between communities. Okay, so of course we need some sort of a mathematical model, and the stochastic block model was introduced in the 80s as a way to generate a random graph based on some unknown underlying community assignments. And the basic idea is that the probability of an edge connection between two nodes depends only on the community that these two nodes are part of. So if you want some notation, sigma, well, so we have k communities, and each node I, where we have nodes 1 through n, is assigned a community. And then the probability that that entry of the adjacency matrix is a 1 just depends on the assignment of node I and node j. Oftentimes, we look at the case of a homogeneous stochastic block model, in which case maybe there's just one probability p that corresponds to within community connections, and there's another probability q that's across community interactions. But you might imagine having something that's heterogeneous, where the probability of connecting inter-community or intra-community for community 1 is like p1, and then you have a p2, and then you have a p12 and or a q12 and a q21. So the reason why this is called a stochastic block model is that if you look at one instantiation of the adjacency matrix, and you actually chunk the community, chunk the nodes into two blocks, so if the underlying communities are labeled A and B, you get sort of a roughly block structure. And here you'll see that nodes within the same community, connecting something in A to something in A, tend to take on the value 1 more than across community interactions. So this might be something like a homophilic, homogeneous block model. And if you looked, this is important maybe for later, if you looked at the expected value of W, what you would see in this case would be a block of P's, maybe a block of P's here, and a block of Q's, and a block of Q's, right? Because the within community connection probability is a P, and across is a Q. So that's the underlying model, and questions that one might ask is, what is a good algorithm for recovering communities? What does it even mean to be a good algorithm? How do we measure this? And that's not really necessarily so obvious. And secondly, we want something that's actually computationally tractable. Because in some sense, it makes sense that you could search over all possible partitionings into k communities, but that would be a very computationally expensive problem. So you want to do something that's slightly more easy. And the question is, under what parameter settings, under what probabilities and numbers of communities and so on, is it actually possible to achieve these rate optimal methods in some computationally feasible way? Okay, so how do we characterize a good algorithm? Well, I'll focus on this one method, which is also called weak recovery. And it focuses on essentially making the fraction of misclassified nodes go to 0. So this is a little bit of notation, but essentially we have an algorithm, sigma hat. Sigma hat operates on the adjacency matrix that we see, W. So we get some community assignment, sigma hat of W. We compare that with the underlying community assignment, sigma 0. We see what the Hamming distance is, so how many nodes are differing, and then we divide it by n, because we have n nodes. So this is the fraction of misclassified nodes. Then you might ask, what is this weird tau thing? Well, this is a permutation, and it actually makes the analysis a bit tricky, because you might imagine that you have some underlying community assignment, which just means that things are partitioned. I mean, we don't necessarily designate one as community 1, community 2, and so on. But if we run our algorithm, you'll probably say these guys go in community 1, these guys go in community 2, and so on. So if you have differences in the labels of the communities, then clearly you want to permute them before you do the Hamming distance measurement. But this is essentially saying how many nodes are misclassified if I just think about chunking up into partitions without labeling the communities. Okay, and this is a loss that we can define with respect to the instantiation of the adjacency matrix. Of course, we can always talk about the expected value. All right, so the expected value says now we draw W from a stochastic block model. So we have these underlying community assignments. We generate a random adjacency matrix, and we look at the expected value of this loss. So the goal of weak consistency is to say, I want the fraction of misclassified nodes to go to 0. All right, so that's going to be our desiderata. So sometimes we talk about having high probability convergence to 0. In other cases, people talk about weak consistency as this risk going to 0. And by Markov's inequality and integrating tail probabilities and so on, you can in some sense sort of shuffle between the two, but it's more like the implication goes in one direction always and in the other direction only with additional assumptions. And I should just mention for completeness that there has been lots of work on stochastic block models, and there are other notions of having a good algorithm. And so instead of having weak consistency or weak recovery, there's this notion of exact recovery. So maybe with high probability, we want the loss to be exactly 0. We want to exactly identify all the communities. And then there's this notion of correlated recovery, which is much weaker. We just want to find some sort of an assignment so that things are roughly correlated. But you can forget about these two because we'll focus on weak consistency for this talk. All right, so the starting point of this project was actually a talk that I heard by a colleague at Penn, Dongming Ma, who is not one of the authors of this paper, but worked on a follow-up of this paper. So we were at the Overwolfak conference, and he was talking about these minimax rates of being able to identify communities. And I hadn't really done any work or thought much about stochastic block models. But he said that his collaborators had come up with this minimax rate on the misclassification error for stochastic block models. All right, and I was quite curious about the right-hand side. So it's minimax, so it has to be with respect to some parameter space and so on. So if you want some details, well, okay, so there's a parameter space, and the parameter space gives you the probabilities of connections, because these are the probabilities, these are the parameters in the problem. And essentially, there's a probability of within community connections, which we denote by A over n, and then there's a probability of between community connections, which we denote by B over n. Earlier, I called them P and Q, but essentially, for some technical reasons, if you care about going down to the threshold, the important parameter scalings are constant over n. Then we can focus on the right side, and the right side has these different variables. So K is the number of communities and n is the number of nodes, but then what is I sub n? So I sub n has this formula, and it's a function of A and B, which makes sense because the hardness of the community recovery problem depends on how separated the probabilities are, right? I said that if the probability of within community and between community interactions is exactly the same, then we can't do anything. But clearly, if these probabilities are more separated, then in fact we can do some kind of community recovery, because we can sort of separate which connections are between nodes in the same community and not. So there's a formula, and you can check that if A and B are more separated, then this thing is going to be bigger, and therefore this exponent is bigger, so the risk is smaller, right? So you get more accurate recovery. But what was curious to me is this. So there's a formula, and it turns out you can write it in terms of an information theoretic quantity. And this information theoretic quantity is known as the Renyi divergence of order 1/2. And I've sort of spent a lot of time around information theorists, but really the only divergences I really think about at all are KL divergences. So I was like, okay, I've heard that there's a Renyi divergence. I've heard that there are different orders, but I don't really know what they are. But suddenly there's some Renyi divergence coming in. So what's going on, right? Because in some sense, you know, the separation between the probability distribution should be involved in how hard the problem is. But why Renyi divergence? Okay, so that was the question. And in fact, this I over n, this Renyi divergence, is very involved in the optimal rate. I mean, one way to look at it is to just stare at this formula. Another way to look at it is to say that, well, this minimax risk goes to 0 exactly when the term in the exponent goes to infinity, right? So depending on whether n times the Renyi divergence quantity goes to infinity, we will have the minimax risk going to 0. So weak consistency, essentially, if and only if n times I is going to infinity. And as I said, the sort of intuition is that the hardness of the problem should depend on some sort of measure of divergence. But so the question is, okay, how general is this, right? So, I mean, you don't have to know much about information theory to know that when you talk about divergences between distributions, you usually talk about divergences between arbitrary distributions, not Bernoulli distributions, right? So a very natural question is, what if I replace these distributions, the within community interactions and the between community interactions, by another distribution? Would that also appear in the rate and the hardness of this problem, right? Or maybe a KL divergence would show up. Or maybe a Renyi divergence of order 3/4 would show up, right? Who knows? So then the question is, what does that even mean? Edge distribution is not Bernoulli. Okay, so this lends itself to the weighted stochastic block model story. So I came back from this conference, and then I asked Baru, and I said, you know, you're an information theorist, so maybe you have some ideas on this. And so we started thinking about it. So here's the motivating example for non-Bernoulli edge probabilities. All right, so this slide is supposed to give some motivation for why we might not just observe an adjacency matrix with 0, 1 entries, but we might observe an adjacency matrix with some other valued entries. Well, one can say that, you know, maybe these types of weighted graphs appear in social networks. You know, not only do we know that two people are friends, but we know that they liked posts on each other's wall 500 times versus 10 times in the last year, right? And so there's some more information that's sort of encoded in the strength of the connection. Airline networks. So we might have cities that are connected by different airlines, but maybe we want to say that some of the cities are connected by this particular airline versus that other airline. So it's not like we just know that things are connected. We know something about the nature of the connection. Here's a biological example. So stochastic block models are used in mapping out the C. elegans nervous system. And I understand that there are different types of connections between neurons. And here they're characterized into 3 different things. So here it's like a labeled version of a stochastic block model. Either the connection is a chemical synapse, a gap junction, or a neuromuscular junction. But maybe in another setting, like a social network, it will be a count. It will just be how many connections, how many interactions were there across this connection. Okay, so to abstract things, instead of just having 2 communities that are connected by edges, we have 2 communities, or maybe more communities, K communities, and they're connected by colored edges corresponding to the type. Or maybe they're not colors, maybe they're just continuous values. And now instead of saying that we have a within community connection probability of A over n corresponding to a Bernoulli A over n distribution, we have an arbitrary distribution Pn that governs the probability of, or the probability distribution that corresponds to those entries of the weighted adjacency matrix. And then we have some other distribution Qn, which is the between community interactions. And you know, one thing you could do, which is actually what's done in a lot of modeling cases because the unweighted stochastic block model has been studied so much, is to say, let's just forget about the colors or the labels of the edges, right? So let's take our social network, and we know how many times people interacted across each friendship link, but let's just treat all the friendship links as the same, And you could then do community recovery, and it will probably be informative. But maybe you'll lose some information, because these knowing the nature of the edge labels might actually give you some information. Okay, so first we'll look at the case of discrete weights, and then, as I said, we'll proceed to the continuous case. So in the discrete case, we can think about all of the edges as being colored different things. And you saw a picture of that earlier. And recently I heard a talk on what are known as multi-layer networks, and it occurred to me that this is also a case of discrete weights. So let me just illustrate, because this might be interesting. Think about this as an airline network. So we have a bunch of cities, and they're separated into 2 different communities. And we know that this is the connectivity according to one airline, this is the connectivity for a different airline, and so on. Right? And so you can say, well, put them all together. But it's not that simple, because there are certain edges that are multiple colors. Okay? But you can also think about this as saying that let's come up with a new labeling system where we have 2 to the m different possible values. So if we have m different airline networks, then we can compose these all into some discrete distribution taking on 2 to the m different values, where we have a different label depending on the number on the subset of layers that it's a part of. Okay, so this is another case of where we might care about discrete valued edges. Okay, so what do we want to do? Well, remember that our overarching goal is to come up with some sort of good method for recovery. And the key point is that we can leverage what's done in the unweighted case, but we have to do it in a smart way. So let me give a very short summary of certain types of algorithms that are quite popular for unweighted stochastic block models. So when you have just a 0, 1 adjacency matrix, what can you do? Well, the first thing you might try is maximum likelihood. But as I said, you kind of need to search over all possible cuts of the n nodes into k communities, which is sort of difficult. And of course, if we try to do maximum likelihood and we have a weighted stochastic block model and we have different labelings of edges, then it's going to get even more complicated. So we don't want to do that. Then there's this very popular method based on spectral clustering. And to be honest, when I first read about this, it didn't make a ton of sense to me. Then I taught a class on spectral methods, and now it makes a lot of sense. So why does spectral clustering work? Well, it comes down to the fact that when I gave that picture of W earlier with 0s and 1s, the expected value of the matrix had these nice blocks, which is like P, P, Q, and Q. So what you want to do is you want to apply spectral clustering to the columns of your adjacency matrix. And the idea is that the adjacency matrix is going to be fairly close to the expected value. The expected value is exactly in 2 clusters, because the columns are either P, 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 Q, 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 or they're Q, 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 P, P, P. All right, so that's kind of why spectral clustering works. And there are various nice results to show theoretically that what I said is true, that W converges to the expected value quickly, and therefore you can just apply spectral clustering and we'll give you weak recovery. But another important thing, so this is sort of important for later in this talk too, there's a difference between getting weak recovery, which is saying that the proportion of misclassified nodes goes to 0, and getting the optimal error rate. Right? So the optimal error rate is what could I do with the best possible algorithm. I don't just want the proportion of misclassified nodes to go to 0, I want it to go to 0 as fast as possible. And there's this nice paper by Chao Gao and collaborators, including my colleague who I mentioned earlier. And they showed a way to go from the initial spectral clustering method to get the optimal error rate. So in some sense, you first do some rough clustering based on spectral clustering. You get something that makes the error rate go to, makes the number of misclassified nodes go to 0, and then you use something that's sort of like a local maximum likelihood calculation to refine things and get a better clustering. And this you'll see a little bit later in our algorithm as well. Okay, so here's a note. So as I said, what we want to do is use some sort of method that works in the unweighted case and maybe apply it in a smart way to the weighted case. So if you were to just look at the slide, you would say, maybe I want to do spectral clustering to my weighted matrix. Why not do that? Because it's a somewhat reasonable thing to do. But one sort of intuitive sense for why this is not quite the right thing to do is to say, well, okay, so I have a weighted adjacency matrix. So imagine I have that colored graph like before. Then I need to arbitrarily assign numbers to those colors, right? So like green could be 1 and red could be blue, red could be 2 and blue could be 3 and so on. But that's sort of arbitrary. But that's certainly going to affect the nature of W, right? And so in some sense, I shouldn't just be naively applying spectral clustering to some weighted version because I've just arbitrarily assigned numbers to colors. So that's probably not what I want to do. But it turns out that spectral clustering is useful as sort of a subroutine of the overall algorithm. All right, so what do we want to do? Well, as I said, we want to recycle these methods that are used for unweighted case. So the first thing you might do, which I said was not necessarily a good idea, is to just drop the colors. Drop the colors and do some recovery method for an unweighted graph. And if you're lucky, then you'll still recover the communities. Another thing you could do is you could just say, well, I'll focus on a certain color. And then I'll apply the same method. So I colored these blue to respect the color from before, but imagine that these are just black edges. All right? So I pick one color, and then I cluster, and I get some assignment. So, okay, well, then the question is, what color should I pick? And do I know that there's always a color that works? Well, these are not very clear. So could something that's simple like this actually lead to optimal estimation rates? Well, it turns out that with some tweaks, yes, but we should be smart about it. The other question is, what kind of reduction do we want to do? All right. So in that direction, we need to ask ourselves, what do we mean by optimal rates? So this isn't exactly the way that the analysis, or that that we approach the problem. But from a pedagogical point of view, to try to understand what is the optimal rate, it turns out that some modification of the earlier minimax rates for the unweighted case can be used to at least to get a lower bound, which is actually sharp. So if you believe that, and that actually took us quite a bit of work, then you sort of know something about how hard the problem is. Maybe. You at least know a lower bound on how hard the problem is. So certainly if you want to make the risk go to 0, then you should make this term in the exponent go to infinity, right? We discussed that earlier. So if you want to make your risk go to 0, then you should have n times I going to infinity. All right, and you can check that actually if you simply drop edge weights and cluster on a particular color, you're not going to get down to this rate. There's still a gap. So something maybe harder should be done.
Yeah. What is IN here?
IN is this Renyi divergence between now Pn and Qn, which are these arbitrary distributions. So earlier there were Bernoulli distributions, and now there's some arbitrary Pn and Qn. Could be a Gaussian distribution, could be, well, I guess for this half of the talk, it's like a multinomial distribution, for instance. Right, so there's more work that needs to be done in order to actually get this lower bound in the arbitrary case, but it can be done. So we at least have some sense of maybe a limit on how hard this problem is. All right, so now I'm going to, I'm trying not to get too lost in the formulas, but here's an observation. So it turns out that so here's this IN thing again, right? So for an arbitrary distribution, Pn and Qn, so here we're talking about discrete distributions. So we assume that Pn and Qn are supported on L+1 values, okay? And you can write out in the setting where the divergence is going to 0. So in some sense, we're looking at the threshold of how hard this problem is. So we're interested in the limits of when it's possible to cluster and not cluster. So the regime we care about has to do with when the divergence is going to 0. Okay? And it turns out that in that setting, you can actually expand out or rewrite the term, the expression for the Renyi divergence in the following way. And this is also known as a Hellinger distance. So there's kind of this, this nice relationship between a Renyi divergence and Hellinger distance, but that's not too important for now. But what I do want to point out is the following. So I argued earlier from looking at these lower bounds. So here I said, if we want this risk to go to 0, then this term had better go to infinity, right? So we're going to focus on the setting where n times In goes to infinity. Okay, so the point is, if n times In goes to infinity, then there must exist some label or some color such that the term goes to infinity. So let's look back here. So I'm saying if n times In goes to infinity, then that means that n times this sum of L+1 things goes to infinity. So if L is finite, so if the number of colors is finite, then at least one of these terms goes to infinity. And it turns out that simply by looking at the theory for the unweighted case, that means, well, it's an if and only if statement. So if this happens, then in fact community recovery based on this particular privileged color L star will give us weak recovery. Remember, weak recovery means that the fraction of misclassified nodes goes to 0. It does not mean optimal error rate, but at least it gives us some nice consistent clustering. All right, so natural questions. First of all, how do we find L star? Because we're not told which one it is. We get a colored graph, right? And the second thing is, well, just getting a weakly consistent method might not give us the optimal rate. So what should we do? What sort of extra work do we need to do in order to actually achieve the optimal rate? All right, so this slide I'm just going to go through quickly. I want to convey some sense, but maybe not have you remember all the details. So this is the procedure. So essentially, you have these L different colors, and what you want to do is you do a clustering based on each one alone. Because as I said, we're sort of reducing to the case of the unweighted stochastic block model. So the first thing we do is we say, let's just look at the red edges, then let's look at the blue edges, and let's look at the green edges alone. So we end up with capital L different clusterings. Okay, so based on a particular clustering for color L, now we're going to estimate the within community connection and the between community connection. These formulas are not important. That's just what you would expect. So you take a color, you cluster, and you have a bunch of connections now that are within the same community, where your communities are defined according to whatever clustering you had. You calculate the empirical average, and that's your within community connection probability. And then you do the same thing for between community connections. And these are just scalar values, because in the unweighted stochastic block model, we just have a P and a Q, not a distribution Pn and Qn. Okay, so these are the within community and between community connections. And the choice for L star, it turns out, is given by this value. You can think about this as a chi-squared distance. If you don't want to be so technical, you can just think that, I mean, the right color should be the one that sort of gives you the maximal separation between the within community and between community edges, right? So in some sense, what you want to be looking at is something that gives you the maximal separation between your empirical P hat L and your Q hat L. So it turns out it works, and it turns out that you can show that, in fact, an L star chosen in this way gives you a weakly consistent initial clustering. All right. So, but as mentioned before, we have to work a bit harder to actually get the optimal error rate. And in fact, we have to work a lot harder. So this slide, I think I might go through even faster than the previous one, because honestly, it's the type of thing that you'll stare at a while and still might not make sense, and then you stare at it again, and eventually it sort of makes sense. So the basic idea is that just as in the unweighted case, we kind of adapted this method from the paper by Chao Gao and co-authors that went from a weakly consistent initial clustering to a more refined one. And I mentioned this notion of local maximum likelihood. So let me just put up a picture and a formula, and you can look at whichever one you want. So the idea is you don't want to do maximum likelihood on the entire stochastic block model, because that involves partitioning n nodes into k communities and searching through everything. But you can do maximum likelihood just on one node alone. So imagine that we have a community assignment of all the other nodes except the one that you're sitting at. Then maximum likelihood just says, let me search over all the capital K possible assignments of this node. And that's something that you can do computationally tractably. You can also do that for all the other nodes. So the insight of Gao et al. Is to say, well, do some initial clustering on all the other nodes. So do a leave one out type of estimate, and then use some local maximum likelihood estimate. And of course, maximum likelihood in this sense, in this setting, also depends on the probabilities of particular within community connections, between community connections, and now the colors are mixed in. And it turns out that what you want to use here is these estimated connections based on L star. So that's why L star was important. Your initial color had to be reasonably good so that the assignments that you're using to calculate this approximate maximum likelihood are pretty good. And then you'll go around and you'll find these clustering assignments for everything else. And then you sort of need to combine them. So that's the very, very brief overview. So maybe the keys are some local maximum likelihood after the initial weak recovery, and that gives you the optimal rate. All right, so this is the type of result that we get. And so again, you don't need to stare at this too much, but there are two important assumptions. One is that, in fact, your two distributions are converging together in this sense of the Renyi divergence. And the other one is that n times the Renyi divergence should be going to infinity. Because as we said, that's what we need in order for that lower bound to vanish. And this is a high probability result. This says that the probability that the loss is smaller than this character that showed up earlier is going to 1. Okay. And I want you to focus on this Renyi divergence. So this IN is showing up again. Now, you might complain a bit because this doesn't exactly look like a lower bound on risk. So earlier I had a lower bound on risk, and I want an upper bound on risk, and that's not quite right. So as I said, you can sort of shuffle between that sort of high probability bound and the expected bound, sort of by integrating tail probabilities. Turns out that you can get this under some extra assumptions. And I'm going to gloss over the details here. Essentially, there's one regime in which you get exact recovery anyway, so that's the easy regime, so we're going to throw that out. And in the case when exact recovery is not possible, but weak recovery is, then in fact we get a matching upper bound. Okay? So at the end of the day, In fact, we have this exact characterization of the minimax risk in the case of weighted stochastic block models, and it's governed exactly in the same way by the Renyi divergence. So that case is more or less closed. Okay, but that's not the end of the story. Actually, for me and Vernon, that was sort of the end of the story, because we're like, great, it works out that the Renyi divergence shows up again. Of course, we really set out to look at things like Gaussian distributions, or even the infinite colored case, so maybe L can grow with N, but we didn't quite know how to tackle that, and it seems kind of tricky. So then Min entered the picture. So Min started his department postdoc at Penn, and Min likes non-parametric estimation and so on. So he's a perfect person for the job. Okay, so just to emphasize, now we want to look at a case where you have weights that don't just come from discrete colors or labels. So imagine Gaussian data. So your entries of your adjacency matrix could be negative even. Okay. And I should say that work in this area was quite scarce. Even in the case of the labeled stochastic block model, it was fairly scarce. And very importantly, there was always a parametric assumption. So it's like you have within community connections and their normal mu1 sigma, let's say normal mu1, 1. And then you have between community connections and their normal mu2, 1. And as long as mu1 and mu2 are sufficiently separated, at some rate that might be converging but still has some separation, then you can in fact do community recovery. But it turns out that our method is non-parametric, so we don't assume a parametric model, and it still is in some sense rate optimal. Furthermore, it's computationally feasible. It's rate optimal. So what's the basic idea? Well, okay, maybe I'll say the basic idea. The basic idea is reduced to the labeled case, reduced to the discrete case. So essentially, you have your continuous distributions and you discretize properly. Of course, discretizing properly is very, very challenging and technical. Okay, so what is our setting? Well, now our setting is, I mentioned two different Gaussian distributions, but you might actually care about a case when you have a mixture distribution. So, I mean, maybe you have Gaussian edge labels, but you actually want to just look at a sparse graph. So first you create some sort of a sparse graph, and then you label the edges that exist with some Gaussian, with a draw from a Gaussian distribution. So for that reason, we actually studied a case where the within community connections have some point mass that's given by P0n, and there's some density that's the continuous density. Okay. And in particular, so we don't just care about the sparse graph setting, we also care about the dense graph setting, where your entire adjacency matrix is completely dense and you have draws from the Gaussian distribution, but this encapsulates both of them. And the sparse graph setting says that the probability of the point mass is going to 1. Okay, so now we have this character, Renyi divergence. At least that's what we want. So we found that there was a Renyi divergence that was relevant in the case of labeled edges. And the question is, does it continue to persist in the case of continuous edges? So it turns out that you can also write something that looks a little bit like a Hellinger distance. And it looks like this. So I wanted to draw your attention. Min was very happy when he wrote this formula because it's extremely clear in one sense. So these are the probabilities of the point masses, right? The capital P0s and Q0s. And what you get in green is what you would get if you simply ignored the weights on the edges. So you simply said, look at this graph and look at what edges are there, and forget about the fact that I have these draws from a normal distribution sitting on the edges. Then the separation you get is exactly this. This is that Hellinger distance term we had earlier. And then there's another term. And the other term brings into play the separation between those continuous masses. So you see that, the punchline is that the Renyi divergence characterizes the error rate. But you see that if you ignore the edge weights, you're basically ignoring the extra separation that you get from the second term. All right? So, I mean, you could be in a setting where the probability of seeing an edge, if you just ignore the weights, is exactly the same for within community and between community connections. Then this green term is 0. So if you ignore the blue term, then you say there's no separation. But, what if your continuous distributions have two different normal distributions? Then you want to take into account the fact that if you actually see the edge weights, you can do some kind of distinguishing. All right? So this sort of isolates the effect of completely ignoring edge weights, which of course you don't want to do. All right. So now, as I said, the main idea is to apply the technique that we had for labeled case. But again, it's very tricky. So the issue is that the analysis I gave earlier depended on the number of colors being finite and not growing with n. Remember, I had this sum of L terms, and I said that if the entire thing goes to infinity, at least one term goes to infinity. Unfortunately, that's not going to be true anymore if L is growing, so if L is indexed by Ln. But as you might imagine, if I have a continuous density and I want to approximate it closer and closer, the number of bins is going to have to increase. So this is where a lot of extra technical work comes in, but in spirit, the same sort of story holds. Okay, so what we want to do is we want to take our continuous distributions and we want to chunk them up appropriately into discrete bins. So there's sort of two settings that we looked at, and the first setting is to say if the continuous weights have a bounded support, which of course is not true for Gaussians, but it might be true for some distribution, then the correct discretization is to just use equally spaced bins. Of course, there are going to be regularity conditions on the shape of P and Q, for instance. So for instance, you don't want your P or Q to shoot up at the edges. And in the case when you have a continuous distribution, let's say, a continuous distribution fully supported on the rail line, you want to first do some sort of a transformation to make it in the 0-1 interval and then reduce to the case when things are finally supported. All right, so you do some appropriate transformation, you chunk it into the 0-1 interval, and then you divide it up equal space. Or if you want to think about it, in your initial distribution, you're kind of binning things, but not in an equal way, right? It's like the bins are getting further and further apart as you get further in the tails, which makes sense because, you know, if you were to bin everything equal space up to infinity, first of all, you would have infinitely many bins, and secondly, the amount of information in each bin is getting more and more trivial. All right, so now these slides, the next couple slides, I think I'm going to go through really fast because there's a lot of technical stuff. And I should say that even what I put in these slides is only scratching the surface of the technical stuff that's included in the entire paper. But I want to give some sense of what conditions you need. So the things that we need to consider are what is the proper transformation that we need to do and what is the number of bins that we should choose. So of course there are going to be various regularity conditions. And this is where Min really showed his expertise because, as I said, he's great at non-parametric density estimation. So there are various requirements you would need on the transformation function. And just for some sense, so if you want a transformation function that's mapping the infinite interval into 0, 1, and you want it to be continuous and monotone helps as well, then you can think about CDFs. So it turns out that an appropriate transformation function is the CDF of something. So for the purpose of our analysis, we can just specialize to the case of a CDF of a normal distribution, because why not? Everyone likes normals. The issue is that one important regularity condition is that I think this is the absolute value of the derivative of the log density needs to be bounded, and that's not going to be the case for a normal. So we cooked up some variant of a normal distribution that we analyzed at least in special cases. But our theory holds true if we look at things in the abstract. So there's some conditions we need on the transformation function. Okay, and then again, things are very technical, and there are sort of two different regimes that we need to analyze. So if you look at this Hellinger distance type of divergence between the two distributions, it turns out that you need separate analysis in the case when this is order little o of 1 and when it's theta of 1. And in fact, these are the only two cases that can hold. So I just want to give a flavor of the types of regularity conditions. So you'll see the super technical and then the rough interpretation. So this is the particular case when we are in the regime where this quantity is theta of 1. Okay? And you need, well, first of all, you need the mass that's on the continuous part. Remember, there's a discrete part and the continuous part. You need it to be more or less comparable for your within community and between community connections. Then there's some condition on the tail of phi in relation to the tail of p and q. So the phi is the transformation function, right? And so as I said, when you're looking at the 0-1 interval, you don't want your distribution to shoot up at the corners. And that's why the regularity condition that we impose says that the tail has to be at least as heavy. Then, well, it turns out the analysis is much more simple if you have a bounded likelihood ratio between Pn and Qn. Min was very unhappy with that, so he was able to relax it quite a bit. Then there are even more conditions, so we need something about the derivatives of the log of the distribution. And then, since Min loves shape constraint, he was able to, he said this is the weakest set of conditions he could come up with, and he thought it was quite reasonable. So in any case, you have various conditions. Point is, there are conditions on P, there are conditions on Q, and on phi, and on the interplay between all of them. And then there's a similar set of conditions in the other regime. So what we get altogether is more or less the same theorem as before. So the statement is exactly the same as in the colored case. But what I want to point out is that now we have regularity conditions on the continuous density, because in some sense we're trying to estimate, sort of, the densities. And then we need the densities to satisfy regularity conditions in order to estimate them in a non-parametric manner. And also we need the level of discretization to go to infinity. And we also need the level of discretization to not grow too much, right? Because in some sense, if it grows too much, then everything becomes too coarse. So there's no more separation between our distributions. And it turns out that, well, you can see that if you're assuming that n times in goes to infinity, then if you let ln grow really slowly, like log n or something, then probably this is going to work. But I should also point out that the drawback of this theorem is it doesn't actually tell us, well, it tells us, like, if we know lots of information, what ln should be. Right? If we know exactly how the Renyi divergence is decaying, we know the exact rate, then we can tell you what the right discretization level is. But of course, in practice, you would just do some discretization and hope that it's a slow enough discretization. Okay, and again, you can transform this high probability bound into something on risk. And at the end of the day, you have an exact minimax rate that holds, of course, under these regularity conditions in the case of continuous distributions as well. All right, so let me skip through the examples because I don't really have time to do justice to them, but I should just say I put up a whole bunch of regularity conditions, and of course if you stare at them too long, your head will be swimming because when are these possibly satisfied? But it turns out that, okay, well, there are cases that you can look at when you have a bounded interval, but then maybe more interesting to statisticians, you can look at location scale families, like a Gaussian location scale family or Laplace. So this encapsulates the mean separation case. So I said that we want to do more than just doing a parametric assumption where you have mean separation between your two distributions, but this theory will apply also in those cases. So the point is the regularity conditions will hold, and well, okay, so this is too many details, but you know, if you happen to have a draw from a parametric family, and if the parametric family has a nice property, like it's a Gaussian family or Laplacian or a variety of other things, then you can in fact find an appropriate transformation function and everything goes through. Okay, so let me close with some comments in the discussion. So the first slide is not too interesting. This is just a summary. So, and then there are a few comments I want to make. So the summary is that, in fact, the misclassification error rate is always, well, always with a star, at least under these models that we studied, is always characterized by the same Renyi divergence, whether it's the case of Bernoulli distributions for an unweighted stochastic block model, discrete labeled case, or the continuous case. And we also have a computationally feasible algorithm. I didn't really talk through the details too much, but basically you find this privileged color L star that gives you maximal separation using some very rough spectral clustering, and then you refine it with some method that follows the method of Gao et al. So the two remarks I wanted to make are, first of all, this non-parametric nature. So again, Min was very excited by this, and he worked really hard to make sure that this is fully non-parametric. So most results in the previous literature, they were sparse, but they had to do with parametric family. And what we're doing here is we're getting optimal error rates even without a parametric assumption. So that sounds great. But what doesn't sound so great, and sounds actually kind of weird, is that even if we knew the family that these densities came from, that wouldn't actually help us. Which seems really, really counterintuitive, because if you're used to doing density estimation, you know that you gain a lot in terms of rates if you know that it comes from a particular parametric family. But the key insight that we found, so maybe this is just like retrospective intuition, is that our goal was not to estimate Pn and Qn, right? That was just something that we had to do at some rough level in order to do community estimation. Our goal was community estimation. So the point is that for this community estimation problem, we don't actually need to estimate Pn and Qn to those optimal rates. So in fact, even if you have a parametric family, then it doesn't give you the extra mileage. I mean, you don't need the extra mileage. You can still estimate the communities to the optimal rates. And then the other point that I wanted to make, well, maybe this isn't well, okay, I just wanted to say something about exact recovery, because actually before Min got involved, we were focusing on this exact recovery case, which turns out the analysis is much easier. And for exact recovery, as I said, we just want the probability of no errors to be going to 1. Whereas the weakly consistent thing says that this fraction of errors is going to 0. And in some sense, in the case where you have finitely many colors, it turns out that you can get sharp thresholds in the same way, but it's sort of an open problem for the general continuous case. So as I said, there are various ways of characterizing what makes a good algorithm, and if you measure it in terms of weak recovery, we've closed the case, but in other settings, it might be of interest. So this is just a bunch of open questions. I guess we ran out of steam after working on this very long paper. But you can think about cases where you have heterogeneous connections. So instead of just a certain PN and a QN, you have a different PN for different communities and different QNs for linking across communities. There's also a lot of interest in what are called degree-corrected stochastic block models that deal with heterogeneity in connectivities. We haven't really thought about it. And then another interesting case is, in some sense, our analysis of this increasing number of colors depended on the number of colors increasing in a very slow way. Like I mentioned, ln is like log n, for instance. But you might have a setting where the number of colors is infinite. Like, you know, your values or labels on the edges come from a Poisson distribution, and you don't have any control about that. It's not like you can say that it's growing slowly. I mean, you have arbitrarily large counts. Our analysis doesn't hold in that case. So, I mean, does a Renyi divergence show up? I don't know, it could. So that's it. I would say the first paper is sort of preliminary work that dealt more with the exact recovery setting. And then this very long but very nice paper, I think, and I give all the credit to Min, or most of the credit, just went up on arXiv last month. So thanks for your attention.
Have one quick question?
Quick question. So in your analysis, you assume K as a fit, right? So is it possible when your sample size increases, the number of clusters may increase?
Right. So in our analysis, we did assume that K is fixed, because I think the technical details were getting quite complicated already. But in the paper for the unweighted case by Harry Zhou and his students, they allow K to increase. So actually, instead of n times I going to infinity, they need n times I over K to go to infinity. Yeah, and probably the same thing would work here, but I think it would just add another layer of complexity in the calculation.